Now the next example is this finite wave train. We could do that at the same time. No, different F. This F is this sinusoidal, except it's truncated. It's omega sub 0 t what t is within this you see, suppose that the n is capital N is a large integer, and zero otherwise. Zero is greater. Okay. So you just make the same thing, just do 3 times 5. That's the omega square 2 pi. Let's put it in here, but now because of the truncation, you can now set the limit and over when the f is non-zero, so it's minus n omega sub 0 to n omega sub 0, and just keeping the first case. Right, and that is straightforward. And then now you can choose to do it either way. If you like, you can express sign as the e to the I omega sub 0 t minus e to the minus sub 0 t divided by 2I. You can use the Euler relation or the inverse of the Euler relation for sign to do the integral. That is slightly easier because of over exponential function. You could do it this way, or you can realize that this is odd function, and you keep the odd part of the exponential function, which is sine I sine omega t, and then use the formula sine A times sine B, that formula, and to evaluate that. Either way is fine. You don't want to look up the formula. So I mean, it's straightforward, and you can memorize that. If you don't memorize that formula, it's better to use exponential function because you all know how to do exponential function, right? So you do it the other way, so yeah.
Does the delta function relation help at all here? Not really.
Delta function is not applied here because of limit.
Oh.
The limit you are not going to infinity. You cannot use that delta function. And later on, you can now justify the delta function formula by let n goes to infinity. And that becomes two terms. One is two delta function because sine has the two terms. Go back to exponential function. So we'll just do I, and then limit, and then let e to t minus e to the minus e to substitute t, and then multiply by right. And quite obviously, you just by this consideration, you know that the final answer should be purely imaginary because you pick up just the I sign term, but later on we'll get that out by this method also. So there will be two terms. One is this times that, and do the integration. You have e to the E divided by I. And evaluate at the limit. It's a lot of value. Actually, the second term is also the same minus, except that now is we have omega minus and then divided by I. And evaluate at the same two limits. Okay. Now, when you evaluate at these two limits, obviously that becomes sign, right? Because upper limit function, lower limit is negative of the same argument, and now you have the rest. I mean, I will come add up to the exponential sign function. If you have two I, put the two inside, two I of this minus the complex conjugate of itself. So, two over here, so you have I. And the rest is just sign of two. And the rest is the same. Okay. See if I get it correctly in the textbook. Yeah, the textbook has this I because textbook using the Fourier sine series. You don't have to do a Fourier sine series because it's just the same. Okay, so oh yeah, I forgot this. Evaluate at n pi. T is n. Okay. Then it should be the same. Except this I thing, and then the sign is coming to the I. Just but the yes, yeah, the property of this final result is that the second term will hit assuming omega sub 0 is positive, because we already defined that if negative, you don't have this formulas. If omega sub 0 is negative, so the argument of the sine function or the denominator will hit 0 at omega equal omega sub 0, right? But the first term doesn't have that problem because omega. I mean omega. If you can take negative omega, that negative omega equals omega 0. So there's some symmetry in the because of the function is real, then the Fourier transform has the property that I think one exercise already asked you to show that for a real function, the Fourier transform has this property. You change omega to minus omega, just take the complex conjugate. Okay, right. So you can check that. Change omega to negative omega. And this term change to this term. And, right. Except the negative sign, but then I change the minus I. You take the complex conjugate. Okay. So anyway, so you can consider this as one of them. Just consider positive omega. The same discussion applies for negative omega using this consideration. The positive omega, then you hit the 0. And but this is not truly singularity. It's called removable because you have a sine function of the same argument. So one small argument, so you cancel this omega minus omega sub 0 factor. But still, in that case, the argument gives you n pi over omega sub 0. So when omega tends to omega sub 0, this one is proportional to n. And assuming n is positive, a positive large integer, then this term will be large. And the rest, this is just sinusoidal. So just the absolute value or the magnitude of sign for this first term is just between 1 and -1 to 1. And then the denominator is not large because omega not close to omega sub 0. So you can work out the graphs like the textbook. So omega, when you hit omega sub 0, the magnitude at least is proportional to n. So this is like n, the n pi of omega sub 0 divided by 2 pi square up to the n pi 0 over the 2 pi. So the magnitude, at least look at the magnitude, right? And then when omega is not close to omega 0, that one fall off. So you have the will be small somewhere outside. And now the width of this is when it hits 0, when this function hits 0. And when it hits 0 is when at the location omega minus omega sub 0, this is omega minus omega sub 0 times n pi over omega sub 0 equals to pi. The first one is pi. Right? Or in that case, omega minus omega sub 0 is cancel with pi, so omega 0 over n. And what large n is very small. So that's just a little bit away from omega 0. So this is omega 0 plus omega 0. Yeah. Likewise, this is minus. That will hit 0, and then you oscillate. Right? And so this is highly peak function if n is large. Right? So that is a general property. So when n is large, which means this wave train is long. This is if you have a really long wave train from minus n by this is 0 to this is along omega axis. No, along the t axis. There's a wave train, like something like that. And that for a long wave train, then the peak will be very narrow, and the peak is tall, but the width is very narrow. Okay, and so that's the general property, and we call it so-called uncertainty principle. Okay, that's inverse formulas, and you can look up the inverse. So the inverse Fourier transform is just like a Fourier transform. If you transform a very peak function, you get a very broad spectrum. But if you Fourier transform a function that has a very broad wave, or in this case, a very large wave train, then you get a very short pulse in the Fourier transform. So that is a general property in the Fourier transform. And you can also see it from the delta function argument. Just you can say that this is a Fourier delta function. This delta function is like the Fourier transform of just one. Right, -2 pi into the minus e to the I. Right. This is like the Fourier transform of a magnitude of 1, or in this case, a square of 2 pi, or 1 over square. Right. Yeah, this is a constant, and you take the Fourier transform by a constant, you get a delta function. The delta function is highly peaked, so basically the function itself is just a constant, the ft. Right? Then the Fourier transform G over here is just a peak. I should say, why is it the similar thing to have a truly broad function, which is just a constant. You get exactly a peak, infinitely peak function, a delta function. In this case, it's a long wave train give you a highly peak. Similar, okay, but this is a general property.